As we all know, this right here is a complex number, and people have different preference. Some people like to put their complex number inside of a square, and they get this. Some people like to put it on the bottom, and they will have this. And some people also like to put it inside of the square root, and see the description. My question for you guys is that, where do you like to put your complex number? Leave a comment down below and let me know. And if you don't have a preference, don't worry. In this video, I will give you guys 3 places. I think they are really cool for you to put your complex number, alright? However, notice that this right here can actually be done by algebra. If you want to have some new places to put your complex number, you have to look at what we call the Euler's formula. So have a look right here. So we have e to the I theta that's equal to cosine theta plus I sine theta. With this, you can actually do a lot more. Have a look. First, have a look right here. This is a complex number to the second power. We have that already. You can just multiply it out, right? How about let's switch the place. 2 as the base and the complex number as the power. So have a look. This is my first place for you guys. Let me write it as 2 raised to the power of a plus bi, like that. And in fact, you can put in any real number for the base and the following still work. You can put down x as general formula, but let me just use 2 for this. Alright, here is what we can do. First, we have a plus bi in the power, so we can write this as 2 to the a times 2 to the bi, right? Just break it apart. And when we write a plus bi, a and b are real numbers. So in this case, 2 to the a is real. We just have to fix 2 to the bi power, right? Well, so far we only have this, which the base is e. However, the base right here is 2. But don't worry, we can do the following. Have a look. Let me keep the 2 to the a the same. But instead for the 2 right here in red, I will purposely write it as e raised to the ln 2 power. And of course, e and ln cancel, we still end up with a 2 right here. This is the new base now, and then we raise this to the bi power. And the reason is really that we want to utilize this formula, base e, right? Now, this and that we can just multiply. So we see this is just nicely equal to 2 to the a times e to the, let me write down the I first. So I and then b and then ln 2. Like this. Now, 2 to the a is still good, just leave it. And for this part, I will just write this down. So with a parentheses for that. Well, we'll just have cosine. And then you see here is the theta. So we'll just enter b ln 2 inside of cosine. And then we have the plus I sine. And then theta is again that. So we just have the b ln 2 like that. In the end, if you want to write this in the standard form, you can just distribute, and we'll see that here we have 2 to the a times cosine of b ln 2, and then this times that. Perhaps let's write down the I first, and then we will have 2 to the a, and then sine of b ln 2, like this. And again, you can put down any real number that's positive inside right here, and this will work out very nicely. Unfortunately, if the base is not real, let's say -1 to maybe the a is, let's say 1/2, you end up with more complex number that's not preferred. So, first place for your complex number. Alright, now, let's see what else we can do. Well, we talk about e to the something. Let's talk about its inverse, namely the natural log. Yes, let's put the complex number in the natural log and see what happens. So, second place, I'm going to write this down right here for you guys. Let me just have ln of, and inside is going to be the complex number a plus bi, like that. Wow, what will happen? Let's see. Well, here's the thing. A plus bi is what we call the standard form of a complex number. But I really want to use e because ln and e will cancel each other out, which is going to be very nice. And hopefully you can utilize this formula. This is how. let's take a look at the complex plane of the complex number a plus bi. So here is a picture real quick. So suppose here is the point, and let's say this is the real axis, and let's say this is the imaginary axis. Then this point represents a plus bi, like that. What does this mean? This means you go from here to here, a, you go from here to here, that's b, like that. Great. But we can also represent this point with the polar form. You just have to tell me two things. The first thing is let's do the distance. The distance from here, the origin to here, denoted by r. And the second thing is the angle from here, you turn so much to here, denoted by theta. Have a look. Based on the r and theta right here, we can write a as the hypotenuse, and because this is the adjacent side, so we can put down as cosine theta. Similarly, b will just be the hypotenuse, which is r, and then we have the opposite sign right here, so that's sine theta. So that's pretty good. And now have a look. If we have a plus bi, well, this is really the same as, put this down for a, so we have r cosine theta plus b, which is that, namely r sine theta. So that's what we have. In the end, we still have the I, so let me just put that down right here. And the I is outside of the sign. Well, both of them have the r, so let's factor that out. So we see this is equal to r parentheses, and this inside is just cosine theta plus I sine theta, like that. Well, here, this is just r. But what's this? This is nicely equal to our Euler formula, and that's exactly e to the I theta, like that, which is very good, of course. Well, you can actually write a formula for r in terms of a and b, because the r is just the distance from the origin to this point. So if you would like, you can say r is equal to the square root of a squared plus b squared. Man, I have a video from 2017. I forgot the square root. If you know which video I'm talking about, leave a comment down below. A worse situation. I put down capital R right here, and I put down capital C right here, which is again a horrible mistake. So if you know which video I'm talking about, leave a comment down below. But anyway, you can write r in terms of a and b if you would like. Similarly, you can also put down theta as a formula with r tangent in terms of a and b, but let me just keep it as theta right here. Alright, we are not exactly done yet though, because the following. Have a look. Earlier I just said from here to here, that's the angle theta. But the truth is, you can really continue, rotate, let's say this way, meaning you can just add 2 pi to it, and sine and cosine, if you add the angle with 2 pi, that's the same thing. Similarly, you can just keep on going. And some people don't like to turn this way, they like to go backwards. So you can also rotate it backwards. So the way to fix that is, you come here with the angle theta. What you'll do is, you just have to add the angle with 2 pi and let's say k. K is just an integer. Similarly, you will have to do that right here. And this will be the same as the original, right? And in the end, you will just have to put this down right here, plus 2 pi k. And if theta is in between of negative pi and positive pi, which is pretty much this rotation right here, well, that's what we call the principal value of that complex number. But you can actually have a lot more values. That will be for another video maybe. But hopefully this is okay so far. And now, I'm excited to put this down instead of the ln, because things will cancel very nicely. Have a look. Now, we're looking at ln, and the inside a plus bi is nicely equal to this, namely r e I, not just theta though, theta plus 2 pi k, like this. And I will also have to indicate that k is equal to an integer, but let me just do that later. Alright, this is ln of r times this. We can break it apart. So this is the same as ln r plus ln of this, e to the I parentheses theta plus 2 pi k, like this. Have a look. What's r? R is the square root of a squared plus b squared, which means r is always positive. That means this right here is always real. This right here is tricky sometimes, because if you have ln of a negative number, too bad, that's another complex number. Very similar to the base right here. If you have -2, -1, whatsoever, to a complex number, that would be a different story. It's not this formula anymore. But we are okay right here, r is positive. So we can just continue. You see that this and that cancel out very nicely. And now we have what? It's just ln r plus, this is just I, times theta plus 2 pi k, like this. And again, what is k? I will have to tell you. K is just a integer. It can be positive or it can be negative. That means you actually have both ways to rotate. Alright, this is wonderful. You have the ln of a plus bi. So another place for you to put your complex number. Alright, let's see what else can we do. Here we have sine, cosine. What if we put the complex number inside of sine or cosine? Let's do with sine and see what happens. So let me just erase this. Here is the third place that you can put your complex number. Have a look. Number 3. Let's look at what if we have sine of a plus bi, like this. Well, this right here is kind of weird. It seems, I don't know. It seems like there might be a connection between this and then the Euler's formula. And the truth is, there is. So, here is the deal. In order for me to continue, I will have to show you guys the complex definition of sine and cosine. You ready? Good. Alright, he's ready. So, here we go. So remember, earlier we have e to the I theta. This right here is equal to cosine theta plus I sine theta. Great. And now, let me show you. I would like to have e to the I, but instead of the theta, let me put it as negative theta, like this. And let's see what will happen. When I enter negative theta in here, that means I will also have to do it here. But cosine is even. That means cosine of negative theta is the same as cosine of theta. So here we get cosine of theta. This right here stays the same, which is pretty good. But when I put this right here, sine is odd, meaning that I can put the negative on the outside, and then we still have the I sine theta, like this. So now, have a look. We have a system of equations. And depends on how you would like this. Well, if we add the equations, you will see that we will have cosine theta plus cosine theta. That's 2 cosine theta. And this will be gone. And we just have to do this plus that. And then we can just divide the 2 on both sides. So you see, this and that is going to be 2, but remember we have the 2. Right? It's just going to be this plus that. So we have, of course, cosine theta is equal to cosine theta, but like, this right here is equal to e to the I theta, and then we add e to the negative I theta. But the 2 I will divide on both sides, so we'll have this over 2, like that. Great. On the other hand, if we subtract the equations, this minus that, they will cancel. We will have I minus negative I, which is positive 2i times sine theta. That will be this minus that, so e to the I theta minus, okay, I didn't say plus, minus. This is negative I theta, but we have the 2i, divide that on both sides, so put the 2i down below here. And these are the complex ways for you to enter your sine and cosine. Pretty cool, huh? However, I do not just want to enter a plus bi right away right here. You will see why. I can actually make this prettier for you guys first before I utilize these 2 formulas. So, have a look and continue watching to see what will happen. Alright. Okay, so first thing first, when we have an angle sum inside of sine, we can actually break it apart with the identity. So let me just write this down. When we have sine of a plus bi, this right here is actually nicely equal to sine of a, right? This is not Sine, this is sine of a, it's not John Cena whatsoever. And then you have to multiply by cosine of the second, which is cosine of bi, right? And then we are going to add cosine of the first, so this is not cosine, this is cosine of a, times sine of the second, so that's what we have. Now, you see, sine and cosine, they are real numbers, so they are good. I just have to enter this and that into here accordingly. And you will see that the number will be working out very nicely. Have a look. Here, sine A stays the same, but let's look at cosine of bi. Well, here the input is bi, right? I will actually have to enter the bi right here, meaning right here, right here. Okay, have a look. First, let me just put down the over 2 right here. And then we will have e, and then this is I. The input is bi, so I really just have to multiply by bi like this. And then I will add e to the negative I based on the formula that we just got. And then we will have to enter bi right here. Yeah, so let me just multiply by bi. Great. Now, let's also continue with the other part. So we are going to add cosine of a. And for this one, well, sine of bi, the input is bi. So you see, I will have to enter bi in here and in here. So have a look. This is going to be all over 2i. And we will have e to the I, and the theta is bi. So we just have to multiply this by bi, and then minus e to the negative I times bi like that. And that's what we have. But have a look here though. In fact, this right here is not a complex number anymore. I times I is -1. Similarly right here, similarly right here, similarly right here. And the only place that you end up with a complex number is the I on the bottom. Well, let me clean this up before we continue. So have a look. Here we have sine of a, and this right here I will just multiply by, and again let me just put this down in blue. We have this over 2. Here we have e, I times I is -1, so we actually just have negative b, and then this right here we just add e to the -1 times negative, so it becomes positive b. So that's what we have. And then just continue, we have the cosine a, so plus cosine a, and then for this part, we will see multiply by the 2i on the bottom, and then this is e, I times I is negative, so we'll have negative b, and then minus, and this times this is negative, times that is positive, so this is e to the b, like that. Very good, huh? Now, do you guys recognize this right here? E to the negative b plus e to the b all over 2. This right here is cosine's cousin, namely the hyperbolic cosine, and the input is b. This right here is almost the same as the hyperbolic sine, but we have to fix this a little bit. Have a look. Right here, we have 2i, but you have to remember, I don't like to be on the bottom, I like to be on the top. So what we can do is multiply the top and bottom by I, so that this right here will produce -1. And this -1 is crucial because it helps us to change this into the right order that we want. Of course, the order of the addition doesn't matter, so we were good. We didn't even have to worry about that. So finally, I will tell you all this right here. Right? Sine of a plus bi, all together, we will have sine of a, and this right here, we'll just write it as cos, namely hyperbolic cosine, and then the input is b, like that. And then we have to add Well, we have the I right here, so perhaps let me just put on I first, and then we have the, actually let me just try to write it down better for you guys, right? So this is equal to sine of A, and then we have cosine with the H, so cos H with B right here. And then we are going to add, here we have the I, and then we have cosine of A, so let's put that down. And lastly, again, this -1 makes the switch, so it actually becomes sinh, namely a hyperbolic sine of. Wonderful! Look at that. This right here, it's the very nice formula for the sine of A plus bi. If you ever want to put your complex number inside of sine, use this right here. Cool, huh? Impressed? Very impressed. Alright, great. Alright, hopefully you guys all like this video. If you have any questions or any comments, just leave it down below. Right? Thank you, and I'll see you guys next time. And as always, bye. Sorry, I did it wrong. And as always, that's it. Bye.